pleasure today to welcome you to March's Center for Math Medicine seminar series, where we have a wonderful speaker lined up. Before we get started, I did want to take a few minutes to recognize the passing of the director of the Center for Math Medicine, Professor Siv Sivaluganathan, who passed recently. I don't want to say too much because lots have already been said about him, but I think it's just important that we recognize he is the founding director for the Center for Math Medicine here at the Fields. He was a leader in Canada in the field for math and medicine. He had many sort of pioneering collaborations with the hospitals here in Toronto. In particular, Jim Drake here, who's a neurosurgeon at Sick Kids, and Amit Oza, who was an oncologist in the, I think, Princess Margaret Hospital here, as well as many other doctors and clinicians here in Toronto that he brought into the Fields Institute and convinced them that math could help in their work, and many fruitful partnerships were formed. So I think I just wanted to say thank you to Siv, and may you rest in peace. And thank you for the legacy that you left to us, which is the Center for Math Medicine here at Fields. So now we will try to switch over to our speaker today. If I can do it right. Yes. So it is my great pleasure to introduce Professor Leonid Hanin. Sorry if I said that wrong initially. From Idaho State University, he is a well-renowned math oncologist. Many people have probably read your papers on TCP and other great works. And I think today you're going to tell us about synergy, the theory of synergy, which is fascinating. So I'm really looking forward to it, and sort of joint actions between radiation, toxins, and medicine. So thank you very much.
Okay, thank you. Okay, so let me start with giving thanks where thanks are due. So Kathleen, Vladimir, and Kostya, thank you so much for inviting me. That's my first visit to the Fields Institute, so I'm really excited about it. I'm going to talk about synergy theory. My first encounter with this subject goes back to 2017, when the journal Radiation Research asked me to review a paper that introduced a new synergy theory. I was quite excited about this paper. The new theory was very, very basic. I even thought that it could have been invented in 18th century. The principal author of this paper is my longtime colleague, Ray Sachs, a retired professor from the Math and Physics department at UC Berkeley. I corresponded with Ray by that time for probably about 12 years on matters of radiation biology and mathematical oncology. I reviewed maybe 6 or 7 of his papers, and when I confessed to him, he reciprocated and told me that he reviewed also many of my papers. I was not terribly surprised, because by that time I knew his writing style very well. So in the fall of 2020, he wrote to me asking if I would be interested in developing the mathematical theory behind the synergy theory that he introduced. And I agreed, and in retrospect, it was a very good decision, because this helped me to maintain some semblance of sanity during COVID times. So Ray's own interest in synergy theory originated from the work he did for NASA. We are all very excited about colonization of the moon and manned missions to Mars. So what is less known to the broad public is that there is a major obstruction to successfully completing such missions, namely galactic cosmic ray. So galactic cosmic ray poses a serious threat to the health of astronauts. Especially, it can cause carcinogenic effects. Galactic cosmic ray is a mixture of various particles, mostly ions, starting from protons, alpha particles, and heavy ions, traveling at the speed close to the speed of light. The origin of these ions is supernova explosions, solar flares, and various events in our and other galaxies. So we produced 2 papers with ray sacs, and today I will be only speaking about the first one. Those are 2 probably latest, or maybe even absolutely the latest papers by Ray Sachs, because he passed away in April 2024 at the age of 92. There was a conference held at UC Berkeley commemorating his life and scientific legacy. I attended this conference and gave a talk there. During this conference, I learned that actually radiation biology and mathematical oncology were the second scientific life of Ray Sachs. The first was probably even more successful because he made major contributions to theoretical astrophysics and cosmology. He worked closely with Roger Penrose, Nobel laureate in physics, and also knew Stephen Hawking quite well. But he never mentioned this to me during our multiple of years of conversations. So what is synergy theory? In very general terms, synergy theory is the study of biological effects of various agents, typically toxins, radiations, and medicines. Theoretically speaking, one can study those synergies and antagonisms mechanistically by analyzing the mechanisms of interaction of these agents. However, it is easier said than done. And the most fundamental difficulties are, first of all, that critical microevents that determine biological outcomes in the target, they are microscopic or ultramicroscopic and quite often unobservable. And also the induction of these changes, primary changes in the target and generation of long-term effects, they work on very different time scales, so that biological effects of these formative microevents may be separated from them by years or even decades. So we will speak about the joint action of some number n of agents. N is larger or equal than 2, and one of the motivations of this work is to extend some things that were done to the case of many agents, because the primary focus as far as applications were concerned was galactic cosmic rays that consists of more than 100 components. Well, reading literature on synergy theory is not a pleasant pastime. It is replete with all kinds of contradictions and controversial ideas and confusing notation and terminology and so on. So in this talk, I'll try to bring some, logic and top-down order into the subject to the best of my ability. So here are some very basic premises. First of all, we assume that dosages of all agents have the same units. The effects are measured on the same scale. And also we assume for simplicity that dosages are delivered effectively instantaneously, like dosages of fractionated radiation. Here are a few hopefully clarifying remarks. So there are 2 classes of agents. Some produce deleterious effects. They're called MEL stresses, and others produce beneficial effects. They're sometimes called countermeasures. So we will assume that all our agents are either produce either deleterious effects or beneficial effects, all of them. In the second article that I put on the one of the previous slides, we studied mixtures of countermeasures and MEL stresses. So typically, a dose of an agent is a well-defined quantity, either physically or biologically. So it is kind of rigid, and so we will be assuming that the only transformations allowed for doses are dilations, like passage from grace to centigrace, and so on. Well, in many settings, effects are also kind of rigid, but in other settings, they're more flexible. So if they're flexible, then basically if, say, the range of effects is interval 0, 1, then any monotonic homeomorphism or diffeomorphism of the range of effects is allowed. Okay, so again, we're interested in synergy theories that are applicable to any number of agents. Well, as you know, it happens so that many theories start with a clever mathematical trick. Synergy theory is not an exception. So basically, synergy theory is a specific ways to devise and justify a formula for the effects of joint action of non-interacting agents as a function of their doses. So that's the trick. Yes.
About function.
Sorry, because they can't hear.
Leonie, I'm just wondering regarding function I, is it integer valued?
No.
Or it can be just.
This function takes values in the range of effects. So typically it is either from 0, 1 or from 0 to infinity.
So,
it's a real number.
So it's a real, positive real number.
Positive, not negative real number, yes.
Thank you.
Sure. So this function I is called the no interaction criterion, NIC. So the way synergy theory works is as follows. Suppose I is an experimentally observed effect for the same doses of agents. So then naturally, if this effect is larger than the effect produced by the same doses of non-interacting agents, then these agents are called synergistic. And in the opposite case, oh, no. And in the opposite case, they're called antagonistic. This is the definition. So synergy and antagonism can be dose specific, as it follows from this definition, but in many cases they're universal. That is, those are properties of the agents themselves and not specific doses of these agents. Now, here is another important remark. In principle, doses of all agents, including the same agent, interact. For example, in radiation biology, these doses compete for sensitive regions of DNA. And if one agent, say, destroys a target within DNA, produces a double-strand break, for example, then the dose of the second agent hitting the same spot is wasted. So there is always interaction. However, we are interested in more specific kind of meaning of interaction, and we will be assuming that no interaction between agents means no extra or unexpected interaction.
When you say observed, when? Because before you were talking about long-term effects. So observed over.
Yes, observed
Not
observed
now,
over
it's not
the
instant
yes,
observation.
observed over the long term. For example, carcinogenic effect.
Okay.
If a dose causes cancer within 10 years, something like this. Okay. So what is the basis for building a synergy theory? Well, the basis is experimentally observed dose effect relations for specific agents. So let's take agent J and denote by EJ the dose effect relation, which corresponds effect to the dose of this agent. So for one agent, when there is no interaction, in principle, this can be measured empirically. And so we assume that we know those dose effect curves. Here are some mathematical assumptions required for building our theory. We assume that all one agent dose effect relations, EJ of D, are strictly increasing continuous functions. And so that the zero dose produces zero effect. We assume that H, the maximum value of effect, is the same for all agents. Just for simplicity, in the second part of the paper I'm talking about, I extended all the synergies theory that we discussed in the paper to the case where the ranges of effect of different agents are not necessarily identical. So all those effect functions have inverse functions, and they're called effect dose relations. And clearly, these effect dose relations, EDRs, have the same mathematical properties as DRs. Here are some examples of dose effect relations. One is the power function. Another is a fractional linear transformation of a power function. This is a very famous Hill model. So for the Hill model, the range of effect is 0h. Hill models are quite useful in chemical kinetics, biochemical kinetics, and studies of gene expression. Another example is linear quadratic function, which is quite popular in radiation biology. So its importance stems from the experimental finding obtained in the 1940s that the number of lethal lesions induced in a cell by dose D of radiation, including double-strand breaks, chromosomal aberrations, is a linear quadratic function of the dose. Well, because we assume that dose effect relation is a strictly increasing function, our model does not include threshold models where effect may be zero for some small positive doses, but we can come close to such by means of example 4. So in example 4, we have this dose effect relation, which is a strictly increasing infinitely differentiable function that vanishes at zero together with all its derivatives. So it is extremely flat at the origin. Okay, some further notation. Well, if we have n agents with doses as d1, d2, and so on, dn, interacting or otherwise, then we denote by E as a function of this dose, the combined effect produced by these doses of the agents. We call it combination dr. Well, geometrically, a combination dr can be represented by a surface in Rn+1. And this is the kind of natural need to visualize those surfaces is the reason why probably 99% of synergy theory was developed for just 2 agents. For 3 agents, you already have to deal with R4. So this function I of D1 and so on, Dn, is the combination dr for non-interacting agents. So that's the only difference between this E and I. I is for non-interacting agents. Well, so we introduce the combination dose, just the sum of all doses, and also dose fractions. Those are positive numbers adding up to 1. So here are two important assumptions. So the first is that the combination DR is an increasing function in each dose variable. The other doses are being fixed. That's a standard assumption in all literature on synergy theory. The second is dose proportionality assumption. We assume that dose fractions are fixed. Well, of course, it is kind of non-assumption rather than assumption, because if we are planning an experiment, we can always deal with radiations with fixed fractional doses. And if we are analyzing experiment that had already been conducted, then we can always stratify the data so that this condition is satisfied. But still, the dose proportionality assumption has very important consequences. The first is that agent doses are completely determined by the combination dose alone, right? Because if those RIs, RJs are fixed, then everything is determined by D, the total combination dose. And also, the combination DR is an increasing function of one variable, right? In this case, under the dose proportionality assumption. Well, the same, of course, is true in the case when the agents are assumed non-interacting. Let's denote by f of I the inverse function to I of D. And so by definition, the decision on synergy or antagonism looks like this. If experimentally observed effect is larger than I of D for the same total dose, or equivalently, if the opposite inequality holds with the inverse function, then this means synergy, and in the opposite case, it signifies antagonism. So this has a very important practical consequence. So then no interaction criterion, which is, as I said, just a combination dose effect relation for non-interacting agents, can be visualized and compared with one agent DRs on the same two-dimensional plot, regardless of the number of agents. So I read approximately 20 papers in synergy theory, and I have never encountered this very simple and natural device, which allows you to compare different agents and view everything on the same two-dimensional plot. Now, here is another important observation. Doses are kind of transient. They come and go, while effects are produced in the target, evolve, and produce some long-term downstream effects. So this means that effects are more important than doses, at least philosophically. And so it is really convenient to view effect as the independent variable rather than the dose. Yes.
Leonid, one more question. Like we have I greater than I of D case and I less than I D case. Of course, we are wondering what happens when I equals IID, I of D. Like, would it be
Yeah,
kind of critical
yes.
case? Some
Well, this, of course, this is rarely happens in practice, but if it happens, you say that there is neither synergy nor antagonism.
Continue.
Yeah, just, yeah,
So it's
yeah,
very
just
rare.
a neutral situation.
It's like almost continuous distribution, like which has a probability equal to zero.
Yeah, yeah, this happens with probability 0.
Thank you. Clear enough.
Thank you, Vladimir. Okay, so here is a picture summarizing what I said. So suppose this blue curve is the function D is f of I. On the x-axis, we have effect. On the y-axis, we have the total mixture combination dose. So suppose that we observe some effect I, and it was produced by dose D. If this point lies below this blue curve, then this means that this effect I was produced by a dose smaller than the dose for non-interacting agents. And so, by definition, this is synergy. Therefore, the region under this curve is the synergy region, and the region above this curve is antagonism region. Okay, so as I mentioned, when we say no interaction, we mean no unexpected or extra interaction. So it makes sense to give it more precise meaning. Where do we put this threshold? So this is a matter of an important litmus test for synergy theory, which is called the Shem combination principle. According to this principle, doses of the same agent are always assumed non-interacting. That's where we put this baseline. Okay, so what I will do next is we will discuss three synergy theories, three major synergy theories. The first is called the simple effect additivity synergy theory. It is defined like this. So n agents, and doses is D1 of D2 and so on. The n of these agents are non-interacting if this no interaction criterion is equal to the sum of one agent DRs for those agents for this specific doses. So the first question is whether this synergy theory passes the Shem combination test. Well, let's look at the simplest case of two agents. Suppose these agents are non-interacting. And so if we have two identical agents, then this function I of D1, D2 is just the dose effect, the value of the dose effect relation for this agent for the combination dose, because that's the same agent. And so according to the simple effect additivity, we postulate this additivity property. This function E must have the additivity property. We also assumed, as you remember, that it is continuous. Well, according to the famous Cauchy theorem that the great Augustin Louis Cauchy published in 1821, every continuous additive function is linear. And so this means that simple effect additivity theory fails the Shem combination test for nonlinear DRs. And nonlinear dose effect relations is a most generic case. Linear happens in practice very rarely and only for small doses. So surprisingly, simple effect additivity is by far the most widely used synergy theory. And still, it does not pass the Shem combination test. This is not a new discovery. It was known more than 150 years ago. The first paper on this subject was written by Sir Thomas Fraser, a British pharmacologist and medical doctor in 1872, believe it or not. And in spite of this, that's the most popular synergy theory. Okay, synergy theory number 2. Yes.
I have a problem to absorb everything, but I wonder, you talk about additivity, what about sub-additivity situation?
Usually the goal of synergy theory is formulate a kind of equation. So which allows you to check whether experimental observations fit a given synergy theory. So
inequality is excluded.
Yes, with inequalities, it leaves too much leeway. Yeah. and biologists, they want more kind of definite situations where they can say that there is synergy or there is antagonism. All right, so the second synergy theory that we'll discuss is so-called Loewe-Berenbaum additivity synergy theory. Walter Siegfried Loewe was a German/American pharmacologist, a very famous one. So he produced this equation number one, in quasi-mathematical terms. And the work around this synergy theory was continued by Maurice Berenbaum, British pharmacologist and biologist, who studied it, applied to many different situations, and popularized this synergy theory. So it is easy to see that the left-hand side of equation one is a decreasing function of I. If I is close to zero, then fj of I. And by the way, fj of I is the dose of J's agent that produces the observed total effect I. Right? We start with observed effect. dj of I is the dose of J's agent that produced this entire effect, regardless of other agents. And so that's the formulation of this criterion. So again, if I is close to zero, then fj of I, the dose is close to zero. Therefore, the left-hand side is close to infinity. So functions fj of I are increasing. So the left-hand side is decreasing. And when I goes to h, to the maximum allowed effect, then fj goes to infinity, so the left-hand side goes to zero. Therefore, we have a monotonically decreasing function descending from infinity to zero, and so this equation always has a unique solution. So this means that this equation defines the no interaction criterion, I, as a function of doses, implicitly. Well, the terminology is as follows. The set of all doses that satisfy equation one, that satisfy the equation E of D1 and so on, and Dn equals to I, where you are not necessarily assuming that agents are non-interacting, is called the isoeffective surface for these agents. And in the case n equals to 2, there is a special name popular in chemistry and biochemistry, isobulb. So according to Loewe-Berenbaum additivity theory, the isoeffective surface for n non-interacting agents is a polytope in an n-1 dimensional affine hyperplane in Rn. In the case of two agents, it's just a segment connecting 2 points on the coordinate axis. Well, it follows from equation one that LBA synergy theory satisfies the Shem combination principle. Why? Because if all agents are identical, then fj of I is the same quantity and it's equal to total dose. So for the total dose, this equation is trivial. Furthermore, the same is true if we consider the same agent, for example, some medicine, a liquid, or maybe a soluble medicine, and dilute it with different dilution coefficients. Then in this case, numerator and denominator in each fraction are multiplied by the same number, the dilution coefficient, and so it is still true. Berenbaum had the idea that this equation one is universal, and he tried to prove this, but David Hand, a famous statistician from Imperial College in London, discovered a subtle error in his argument, and he published a paper about this in 1993. So more importantly is the following observation, that in practice, isoeffective surfaces for two or more agents that are known on mechanistic grounds to be non-interacting, they are often non-affine. So this means that Löwe-Berenbaum synergy theory is kind of too crude. Well, we can rewrite the LBA synergy equation in an equivalent form, because f of I is d. Then if we divide both sides of this equation by d, the total dose, and recall that f of I is just this combination dose, then we get the following equation, which means that f of I is just a weighted harmonic mean of the vector of effect dose relations at the same point I for our agents. And elementary properties of weighted harmonic means imply the so-called betweenness property. It follows that f of I as a function of I, you may think about a curve, f of I lies between the upper envelope of individual effect dose relation curves for our agents and the lower envelope. Of course, the same is true for the inverse functions, which are dose effect curves. Okay, so now here the third synergy theory, which is called hand incremental effect additivity synergy theory. So when we submitted the paper I'm talking about, one of the reviewers wrote to us that that this synergy theory has been already discovered by David Hand. So Ray Sachs' paper was published in 2018, and David Hand discovered this synergy theory along the same lines, basically in the year 2000. However, he published it in a very obscure collection of articles, so people working in synergy theory never knew it for basically till around 2020. All right, so we need a few mathematical assumptions. We will assume that DR functions for individual agents are piecewise continuously differentiable, potentially, except for zero, with no more than finitely many points of discontinuity of the derivative, so that these discontinuities do not accumulate. And we assume that these derivatives, both two-sided and one-sided, are all finite. So it follows from here that the inverse functions, that is individual effect dose relations, have the same properties. Okay, so here is the formulation of hand incremental effect additivity synergy theory. So by definition, if we have agents with given dose effect relations are non-interacting, if the no interaction criterion IFD as a function of total dose satisfies the following autonomous differential equation. So what's the thinking behind this differential equation? Suppose we increase the doses of agents a little bit. Because agents are non-interacting, they do not know about existence of each other, and each agent decide which increment of effect to produce based on the assumption that this agent produced the effect acting alone. And so this increment is the derivative of dose effect function for this J agent evaluated at the total dose, which is this EJ inverse of I, that is FJ, yes. And then, because there are several agents, the real increment of the effect is the weighted sum of these individual increments. So that's the rationale behind the synergy theory. So surprisingly, David Hans and Ray Sachs' arguments were very similar in this respect. Okay, so we all know the formula for the derivative of the inverse function. If we apply it to I, which is the inverse function for E, then we have this formula. And similarly, for every individual agent, because Ej is the inverse function for Fj, then the derivative is this. And if we put this all together into equation 2, we get the following formula, which is an equivalent presentation. So this equivalent form 3 has many advantages. First of all, just from technical standpoint, all functions here evaluated at the same point I, while in the original form, these functions on the right, they are evaluated at different doses. Second, it follows from 3 just like for Loewe-Berenbaum theory, f prime of I is a weighted harmonic mean of derivatives of individual EDR functions. So it follows from equation 3 that Hans' synergy theory also satisfies the Shem combination principle, because in this case, fj's are the same as f, so denominators are all the same, and so it's equivalent to saying that the sum of all those proportions is equal to 1. Well, if in the case where transformations of the range of effect are allowed, it is easy to see that if we transform the range of effect 0h to another range by means of a diffeomorphism, then equation 3 is invariant. It still holds. This is just a consequence of chain rule. However, in the original formulation, it requires substantially more work to prove this invariance. All right. Another great advantage of this formula is that we can solve it for f of I. That's our goal, to find f of I, right? The effect dose relation for non-interacting agents. So we take the inverse and then integrate. The only thing we have to make sure is that this integral is finite. But this follows from, again, properties of harmonic means. So we know that harmonic mean does not exceed arithmetic mean. And so when we integrate this, we get that this integral does not exceed the integral of this right-hand side, a convex combination of derivatives of fj, which is just the same convex combination of fj's themselves. Because all fj's are finite, this integral is finite. And as a byproduct, we get that f of I does not exceed the maximum of all individual EDRs. Or equivalently, the dose effect function is larger or equal than the minimum. So the last question that we will discuss, and that's in this talk, is whether hand incremental effect additivity synergy theory has the betweenness property. So in other words, we have to make sure to claim betweenness property that f of I stays below the lower envelope, or equivalently, the dose effect relation E of D stays, so F stays above the lower envelope and E of D stays above below the upper envelope. Okay, let's look at a couple of examples. The first example deals with a one-to-one combination of two agents. The first with dr d squared and d cubed, So then the EDRs are square root and cubic root. And since we have an explicit formula, we can write the combination EDR for non-interacting agents as this integral. It can be computed by rationalizing substitution, and we get this formula. By the way, what we found is that combination EDR can be computed in closed form, but combination DR cannot. If you set this equal to D and try to solve for D, you won't be able to do this explicitly, right? Obviously. So the advantage of EDR is not only philosophical, but also technical. All right, so here is the picture for this example. Blue curve is the EDR for the first agent, square root. Black curve for the second agent, cubic root. And red curve is this EDR. So you see that the betweenness property is violated. However, we see that there is eventual betweenness. That is, although red curve is not always contained in the region between the two curves, but eventually, that is for large effects, it enters this region and doesn't go back. All right, here is another example. Let's look at a one-to-one combination of two agents with linear quadratic DRs. So for linear quadratic, it is easy to compute. It is easy to compute the EDR and its derivative. So let's look at two cases. In the first case, alpha betas are 1, 0, 5, and for the first agent, and 2, 2 for the second. So in this case, obviously, E1 is less or equal than E2, or equivalently, F2 is less or equal than F1. This means that the second agent is dominant because smaller dose of the second agent produces the same effect as a larger dose of the first agent. Okay, so suppose that alpha betas are 1, 4 and 5, 1. In this case, the two DR curves intersect at some point. All right, here are the pictures. For the first case, we see a kind of perfect betweenness property. However, this red curve, it kind of gravitates to the stronger agent. In the second case, when DRs intersect, there is also a violation of betweenness, but still there is eventual betweenness. So let me make the following comment on violation of betweenness. It is actually a very devastating phenomenon. Let's look at this little curved triangle. If an experimental point belongs to this triangle, then by definition, this means antagonism, right? Because experimental point lies above this red curve. However, if we pass a vertical line through a point within this triangle, then this produces three doses. Dose 1 of the first agent that generates effect I, dose D2 of the second agent that generates the same effect I, and also the combination dose D with the same effect I. But it follows from this geometry that the combination dose is smaller than both D1 and D2. And so a combination dose, which is smaller than each individual doses, produces the same effect. And in intuitive terms, this testifies to synergy, right? So betweenness violation is really a bad property. Okay. So let's ask and answer a few questions about betweenness. So first of all, which conditions guarantee betweenness? Second, under which conditions does the combination EDR curve passes through the intersection point? So if there is an intersection point, then of course, if EDR curve passes below, then betweenness is violated. So what happens if it passes exactly through the intersection point? Can we salvage betweenness in this case? Number 3, does the presence of a dominant agent imply betweenness property? And finally, what about the eventual betweenness? All right, so here is a little definition. So we spoke about dominant agents. Here we need a stronger concept. So we say that case agent is strongly dominant if the derivative of its EDR is universally smaller than derivatives of EDRs for all other agents. Okay. So it is pretty easy to show that in the presence of a strongly dominant agent, betweenness for hand incremental effect additivity theory always holds. And this follows essentially from elementary properties of weighted harmonic means. Okay, so we answered the first question. The second question, suppose two EDR curves intersect. And suppose that combination EDR curve passes through this intersection point. When does it happen? Well, it turns out that if it passes through the intersection point, then up to this point, the individual curves must be identical. So basically, this never happens except for trivial cases. And therefore, the intersecting EDRs, that's a bad omen for betweenness property. Finally, what about the presence of dominant agent and the eventual betweenness? Here is a simple counterexample. Let's look at two agents mixed in equal proportions. Suppose that the first EDR is just I, and the second is a piecewise linear continuous function given by this formula. Since we have an explicit formula for the combination EDR, then we can compute it. It is also a continuous piecewise linear function. Here are the pictures. So the blue line is EDR for the first agent, the piecewise linear black line for the second. So clearly, the second agent is dominant because the second EDR lies below the first one. However, not strongly dominant because on this interval from 1 to 1.1, the slope of the blue curve is 1, and for the black is 5. So it is a dominant but not strongly dominant agent. And you see the eventual betweenness is patently violated. This red curve exits this region between the two individual curves and never comes back. Okay. Finally, there is another bad news about hand incremental effect additivity theory, which is the singularity phenomenon. When I showed this to Ray Sachs, he was livid. All right, so let's go back to the formulation of the synergy theory. This is this first order ODE.
Like 5 minutes.
Yeah, I need less. 2 minutes is yeah. 2 minutes is more than enough. So it follows from the general theory that the solution to this ODE is defined on some interval on 0D, where D is positive. So that's the domain of function I of D, and at the same time, it's the range of the inverse function. Well, and so D is the value of f at infinity, that is given for this integral. So the question is, could it happen that D is finite? That is, can the combination EDR blow up for finite dose? Well, unfortunately, this can't happen. If you look in the paper, there is a counterexample, a little sophisticated one, but not too much. So this singularity phenomenon is possible. That is, if we have regular agents, producing finite effect for any finite dose, then their combination for non-interacting agents may be singular. That is, it may produce infinite combination effect for finite combination dose. And finally, there is still some silver lining. Here is a criterion that prevents this pathology. If this integral is infinite, then this D is infinity. That is, singularity cannot happen. And for example, if there is a strongly dominant agent, then the minimum of these derivatives is the derivative of fk. So the integral of this derivative is fk of h, which is infinite. And finally, this criterion is also free of dose fractions Rj. Okay, so brief conclusions. We spoke about three synergy theories. So the first, simple effect additivity, fails the Shem combination test, and so it absolutely should be abandoned, right? After 115 years, it's already time. So Löwe-Barenbaum synergy theory has, a lot of scientific and geometric appeal. It passes the Shem combination test and has the betweenness property. However, it is not always realistic. And finally, Hand synergy theory also is quite reasonable in terms of its rationale. However, it has a systematic tendency, as we have seen, for betweenness violation, which is really bad, and also may occasionally produce the singularity phenomenon. Thank you.
Okay, thank you very much. Are there questions? Itamar?
The galactic cosmic rays
Yes.
have very low density, right? And high intensity.
Yes, yes.
So they are only one of the agents that you talk about. Or you only talk about them.
Galactic cosmic rays is a mixture of many ions. There are more than 100 species of these ions. And even worse, from time to time, you may encounter ultra-high energy ions that carry the energy up to 10 to power 20 electron volts. This energy is, so that you kind of understand its magnitude, it is 7 orders of magnitude higher than energy ever obtained on Earth in particle accelerators or colliders and so on. So a single ion carries kinetic energy of a baseball traveling at the speed of 100 kilometers per hour. So you can imagine the amount of damage it can do to the spacecraft and to astronauts. And experiments have been made, and they suggest that for a site of the size of a spacecraft, such ultra-high energy particles may be encountered once in a few weeks.
There is very low probability that we are affected by it.
Yeah, on Earth, of course, low, because we are protected by the magnetic field of Earth. Yes.
Okay. So now I'm stuck a little bit about the observed time play effect, because I believe these times are different from different agents. And then comes a question of hidden variable of the cumulative effect of the radiation. Is this theory taking this in account, or it's like ignoring it?
It is applications of synergy theory, especially in radiation and cosmic medicine. It is still in its infancy. I know, and I discussed this with Ray Sachs, there were some experiments on mice where these mice were subjected to different mixtures of radiations. And in mice, cancers arise pretty quickly. So within a few weeks, it was possible to measure cancers in this so-called Herderian gland in mice.
It was noticeable.
Yes, yes, yes. It was noticeable, but the main question of interest to NASA is not the presence of effect. It was known, but the possibility of synergy between different components of galactic cosmic ray. Yes.
To ask, probably it's not relevant for n equal to 2, but if there are many agents, people consider pairwise interaction between them, or maybe triple interaction, or does it make any difference?
You know, there are a lot of work has been done which suggests that just collective interaction between, say, 100 agents is not reducible to pairwise interaction or triple interactions. You know, the number of a large number of agents may have properties in terms of, you know, biological effects different from couples and triples. So what they try to do is to mimic the action of many agents. For example, there were some experiments done, I think, at Brookhaven National Lab, where they studied biological effects of ion beams with 33 components.
Another question is that, so basically we had arithmetic averaging and then harmonic averaging. But did people try something in between? I mean, there are like averages, there's a whole spectrum of averages.
Yes, mathematically you can, but you have to kind of understand what is the
Geometrical
biological meaning of
Yeah.
this.
So
Yeah.
if the clear way -1 would be like harmonic as
Yeah, as you see, harmonic means they kind of came about naturally. Right?
arithmetic is also natural.
Arithmetic is also natural, you know, it's a kind of simple effect additivity synergy theory essentially, but quadratic and others,
Geometric.
geometric, yeah, but maybe geometric is more relevant because if you do logarithmic transformation, then it is arithmetic. But I thought a little bit about it, but did not come with anything productive. Thank you.
I'm having a hard time wrapping my head around the betweenness property,
Between us, yes.
because I thought, like, in the graphs, maybe you can go back to one of the graphs, because I thought we don't want betweenness. If you're talking about the effect of two individual doses, don't we want for synergy the combined effect to be not between the other two curves?
You know, the biological intuition is that if agents are non-interacting, then the dose effect or effect dose function should be some kind of average of individual effects. That's the basic intuition. So this automatically means that for several agents, DR or EDR, the combination DR or EDR should lie between the highest and the lowest, or the upper envelope or the lower envelope. So that's the normal expectation based on biological, you know, heuristics. And so if this is violated, then this is really bad, you know.
So just to put it into, because I'm used to working in terms of very concrete things. So like if we were modeling a chemotherapy and a radiation treatment, you know, given simultaneously, which for like for GBM, for example, we would say, you know, this is the effect of the radiation, this is the effect of the temozolomide. If we're going to give them both together, we should see a better effect. I guess we would assume they're additive, which now you're saying this is not the right way to do it.
Yes, they're not additive, but there may be, you know, a greater effect than from
each
application
individual.
of agents separately.
Yeah, but sub-additive, likely.
Yeah, something like.
But not in between the effect of just the, like if, I mean, I guess it's kind of hard because this is the dose versus the effect, right? I think I'm just having a hard time interpreting the graph, I guess, in terms of how we would model these things.
Yeah, you have to take into account that the combination is a function of total dose. Yes, and
Yeah.
individual are the functions of individual doses. For example, in this picture, you cannot interpret it directly. If in terms of your analysis, you have to take into account that agent one that you apply dose D1 of agent one, D2 of agent two, but when you combine them, then the dose is added.
Right. And the effect should be somewhere in the middle.
Yes,
Of
somewhere
the
in the
two.
middle. Yes.
Okay. Any other questions? Everybody's good? Okay, well, thank you very much for coming to Toronto in person. It's great to have live speakers, and I think this was a wonderful talk and everybody really enjoyed it. So thank you very much.
Thank you.
And thank you for speaking on December 3rd online.
Hmm.
Spoke of you thinking of our talk.
Thank you. It was my pleasure.
That's the talk upstairs. December 3rd. What's that talk?
No, that was in December.
You good?
In December.
December the 3rd, yeah, I gave a talk and then it's.
We're done. We're done.
Great. Thank you so much.
Thank you for coming. See you next time.
Yes.
Many questions.
Because we were working with the They were opening the street, that's it, but then. Yeah, it's kind of changed the game.
The question is, are you coming? Yes, man. That's my guess.
So the trees are there, but they're not. Page four. They're not products.
Yeah, it's these like huge consortium leaders.
So actually, we think. Okay.
Yeah, thank you. And then today, if I leave, I'm gonna ask, like,
There.
I don't want them to.
That way.
Make sure we get it.
Right.
That, like, if people still want it.
Yeah. I don't think I'm on the committee, but
You're not, but
I would like to be on, I would definitely like to be on.
Yes.
I actually had a couple conversations.
Yes.
Like low priority tasks.
No, I think things needed to, people needed to, I
Right,
don't say expire, but you have to rotate.
yeah. Right, I think I would like to be on the committee.
I don't even know what the rest of
Yeah. Yeah.
So maybe I will find out who I need to email, and maybe I can like control you in, whatever. We can kind of, like, I don't want to blow, I want the field to be like, oh, close it.
Right.
So I want there to be, they need them to know if there's interest.
Well, then you can talk to. Shield.
Yes. I'm gonna ask here.
He's my, you know,
Oh, okay.
but I think he was acting director. I just don't know.
I know it's more, but it doesn't.
No, but it's-
Okay, I'll find out and I'll send an email out to CC you.
Yeah.
Show that there's like local support.
I need to talk with that, you know.
Okay, so you can do it online.
Right, well, let me see.
Yes.
Yeah.
Thank you, Adam.
Yeah, don't want to.
No.
Yes.
Thank you.
Yeah,
There's no other things about. I just wanted to say, I was like, at the start, when you started talking about big stocks, it threw me back to my postdoc. I didn't work directly with them, but I was in Boston, cancer research company, and flag. And, yes, yeah, they were very close to the trade. We were doing a lot of radiation, science, photos, radiation, space, NASA, all this stuff. I was there from 2011. It was close. The team, but they were always talking about Ray. Yeah, I can imagine that. I don't want to keep Maybe that's what something. Because there's lots of. Maybe, yeah. So maybe he just got interested in the problems, relating it more. Thank you very much.
Yeah, thank you, thank you very much. Real pleasure. Thank you.
Yeah, I've seen, one of my collaborators, actually, worked with previously on cities, so I had heard of these theories and how there was It's very nice all the time, sure. But it was a very nice, sort of walk through of each one. Yeah, so I work at Robertson's now. It is, we have undergrad. University.
It's a great university.
We have a graduate program, it's small. Most of it, we're very large undergrad. It doesn't. Law school is great, starting. Yes, it's a big. Oh, it's a big university. It's downtown. I mean, it's not as big as you. Very famous for the design, right? Yeah, it's our, it was many. One of the, yes, but it also is one of the largest engineering schools. The law school just like. It's growing. Yeah, they have big aspirations. They're local. It's about 20-minute walk. East side. Young Swedish slide city. The lake is south. Young city west and east. We're a little bit. The center of it. It's a little line. Right.